we'll go ahead and get started. Just as a quick reminder, this session will be recorded. If you're on, please make sure that your microphones are muted. And if you have any questions, you can submit those into the Q&A chat, or you can email those in to info@ninjaag.com, where we will go over all questions here at the end. Please share with us on social media. Our handle is NinjaAg LLC, or using the hashtag NinjaAg. But in our last talk, we really discussed the differences between passive and active NDVI and determining, which is best for your goals on which one to use. And so now that our goal is really switched over to yield modeling and nutrient recommendations based off of this imagery, the active NDVI is really going to give you the most economical value. And so today we're going to take a little bit step further and discuss nitrogen rate and the different approaches to nitrogen rates, kind of how imagery is currently being used with these N rates, and how to practically apply an in season for our management strategy. So why is getting that nitrogen rate so important? Nitrogen kind of seems to always be in the news with states passing new regulations on nitrogen, where like the most recent would be Minnesota, where they're limiting fall applications. And the East Coast has seemed to always been ahead of the curve with these nitrogen regulations for several years. And this is partly because, of the environmental impacts that can be caused downstream. But also partly because of economical impact. Nitrogen can be a big input cost, but it could also impact yield as well if you underapply. But when you apply nitrogen in excess or at the wrong times, this can lead to losses, whether that's denitrification, volatilization, leaching, gases, plant losses, or even surface runoff. And so since nitrogen is mobile, it can end up in the water supply, such as our aquifers, our lakes, or our rivers, or ultimately end up down in the ocean. And you can see this impact, with the Mississippi watershed, where there's tons of nitrogen fertilizer that ends up in the Gulf of Mexico into one of the largest hypoxic zones. But as we're getting new technology in precision agriculture, as more technology comes out, we can minimize these impacts by following 4R stewardship of applying the right source, the right placement, the right time, and right rate. Here are some common methods on how nitrogen is being done today in the industry. Most of these are going to be used to generate variable rate nitrogen recommendations, management zones, or even a flat blanket rate. But, using each of these will have some errors, with their pros and cons, but using one of these is going to be better than your best guess estimate, because we're able to use this data to be able to drive these recommendations. So when calculating a nitrogen rate, these are going to be your main components that most N rates consider. The Stanford equation, where N rate is going to equal nitrogen uptake by the plant, which is typically going to be related to yield, minus nitrogen supplied by the soil divided by a fertilizer efficiency. Now, the Stanford equation was published back in 1973 and is the base for most nitrogen rates being generated today, whether that's a variable rate recommendation or a flat rate. But the challenge is of knowing these numbers before these applications are being made, whether that's pre-plant or mid-season applications. And just think about how hard it is to be able to predict final yield, pre-plant or even in season. How good are we at predicting yield or determining mineralization of nitrogen without taking any kind of samples? And there's many factors and variables that can also impact nitrogen use efficiency alone. So these may seem like simple numbers, but there's a more complex genetic by environment by management components that are involved. And generally, the methods that we discussed or that we saw on our last slide, these are going to involve one or maybe two of these components. Like example, a management zone is going to use, whether that's a crop yield or even a soil components to base those recommendations. So nitrogen uptake is the amount of nitrogen that is going to be removed by the grain or the fiber. Nitrogen in the crop is going to be related to the yield. And so what are some ways that we are determining yield now? So as a yield goal, this is going to be a more subjective, where there's no yield monitor data that's being used. This is going to be more like taking your 5-year average and adding 20%. Yield history would be more data analytics, such as including that yield monitor data or even some stability analysis. Yield zones would be taking that information, that data, and creating zones based on that yield information. But how stable is your yields across that field? Is it always going to be a 85 bushel plus or minus 5 bushel, or is it going to be an 85 bushel plus or minus 30 bushel? And the truth is that yield potential changes year to year due to variability in environment and weather. And since we can't control the weather and yearly patterns can change dramatically, it's hard to be able to accurately determine nitrogen needs based on past yield information. And crop models that are going to be based on a growth curve or patterns, which is going to use weather data and genetics, these work pretty well for predicting yield potential. But is that going to be a site-specific model? If so, how much information is actually going to be needed? Some of these crop models can take into account for a lot of or all management practices that are going to be put into that field, which can be very cumbersome. Cloud-based calculations are able to make this process a little bit more efficient. But the challenge is with that prediction of the future weather, or if we have crop models that are based on historical weather, which work pretty well if you have consistent weather, but who really has consistent weather nowadays? Soil tests are, a good way to be able to determine total nitrogen in the soil, but they're really just a snapshot in time because nitrogen is mobile in the soil. And there's some different methods of soil models that are being based, whether that's with previous residues or percent organic matter, but all are going to mainly include weather, whether that's past or future. And the challenges with this is being able to predict or determine soil nitrogen and when it's going to be available. And so this is the nitrogen cycle that I was taught, where organic matter is the center point of the cycle. And so nitrogen provided by, or in some cases lost by, the soil is going to be dynamic and often weather dependent. And much of the soil nitrogen concentration is going to be controlled by the organic matter. So for every 1% of organic matter in the top 6 inches of the soil profile, there's going to be approximately 1,000 pounds of nitrogen per acre. And there's going to be a really fine line here between your mineralization and immobilization going back and forth here from your organic matter and from what is actually being plant available or not. But once that nitrogen is plant available, what are those weather conditions? Was there a big rain event that's going to wash this down Mississippi, where it's going to end up in the Gulf of Mexico? Did we go through, denitrification over here? Did we apply urea, over here on wet soils, where up to 50% of this can be lost almost immediately due to that volatilization? But also it takes time to be able to collect soil samples, and it takes time to get these results back too. So did that nitrogen change in the soil by the time we got our results back to apply these recommendations? But what it all comes down to is be able to predict the weather. If you're able to predict the weather, we're able to predict nitrogen in the soil. But how good are we predicting weather, months out, weeks out, or even 3 to 4 days out? Historically, there's been an efficiency factor which nitrogen fertilizer is being utilized and was integrated into our nitrogen recommendation, but not provided as an input option. So for an example, the general conversion factor for corn is 1.2 pounds of N per bushel. And it's been shown that corn has around 0.73 pounds of N per bushel on average. So therefore, that 1.2 pound value is assuming a 60% fertilizer efficiency use. And more recently, recommendations have been made to incorporate application methods or timing factors in an attempt to account for these efficiencies. But understanding the nitrogen cycle, where that nitrogen is being applied and what those loss pathways are that we just talked about in our last slide is also big as well. And so what were those soil and weather conditions when that nitrogen was applied? But following these 4 R's have shown to be able to improve sustainability and profitability of an operation. But sometimes our source and our placement is locked in, whether that's due to availability of the fertilizer that's available to us, or even access to our equipment. And so timing and rate is really what our producers must focus on to be able to help improve nitrogen use efficiency. And getting this right rate and the right time is a big part of improving NUE. And so applying nitrogen when the crop actually needs the nitrogen will also improve that NUE, because rain also, it makes grain, but it also washes nitrogen away if it's applied at the wrong times. So now that we've kind of discussed how nitrogen rate is being calculated and what those components are, we're really going to dig into about how imagery is commonly being used with nitrogen recommendations today. So with imagery, we are assuming yield, which is typically like a yield goal based, and even a nitrogen response. Is this green area over here in this field, is that due to a nitrogen response? Does that red area actually need nitrogen? Maybe that green area is a little bit more efficient, but there's nothing really out here to check it. Is this red area, is that a pond or is that bare soil? Not quite for sure. And so there's management zones that are often being created using imagery, where we're taking zones that are created from these green areas, these yellow areas, or maybe these red areas, to apply like a low, medium, and high rate based on a yield goal. And there's a couple of different models on how these N rates are being assigned. So this first model here is going to be similar to like a sandy soil, where we're not really going to apply much nitrogen to that poor crop because it's probably just not going to recover. But we really need to push this better crop over here to be able to maintain yield potential due to a higher demand. The second one would be more like a really good silt loam soil, where we would apply a lot of nitrogen to this poor crop, expecting that crop to be able to fully recover. And we're going to apply less to our better crop because we're expecting it to have enough to maintain that yield potential. Now, neither one of these are wrong, and these are really more regionally specific and depending on the environment and soils of which method would be used. And here is a similar example from a drone company where these relative values were applied. And in this case, they assigned a stair-stepping fashion for the N rate and the NDVI values. So they had these rates in mind here, is 70, 90, 110, 130, 150, that they had already generated. And they assigned them, their higher values to their lower NDVI. And then as they got a better NDVI, they decreased the rate in this stair-stepping fashion. Now, the N rate that it was applied was not based or calculated with using the NDVI. They were assigned these relative values to the NDVI values based on what the agronomist said the crop was needing. And so are they really taking into account for these components of all this, the Stanford equation when they derive these N rates, or was this more of an arbitrary assigned rate? This model uses NDVI plus reference strips to get a nitrogen recommendation that's going to be based on a nitrogen response. So this model specifically is the enriched strip model that we use. And so if the strips are showing up, nitrogen is needed, then we're able to make a recommendation. If the strips are not showing up, then nitrogen is not needed, and this model would say not to apply. And so with the YPN, YP0 model, with the nitrogen uptake, this is the yield potential, which would be specific to each crop and can be adjusted based on regions or even environments. Our nitrogen in the soil, this is our reference strip. This is letting the crop let us know that there is a demand for nitrogen and what that demand is. And these fertilizer efficiency, we're able to use these reference strips to help identify these efficiencies. And so here on this model here on this right side, this is the high NDVI, or where that enriched strip is. So this is yield potential with a limited amount of nitrogen. We're not really going to apply any nitrogen, anything above the enriched strip, because there's a low demand for nitrogen due to the soil nitrogen that's already there. Now, when you get into this middle ground up here at the top, this is that farmer practice, or that field average that's going to benefit for the nitrogen that's being applied the most, and where we're going to apply most of our nitrogen to be able to maximize this yield potential. So these part of the field, it's showing a little bit of deficiency, but we can still reach that full yield potential. And this low NDVI over here, this, for example, this would be like if you had terraces. This is your backside of your terraces, where your crop is, might be poor. So we really don't want to give it very much. We just want to be able to give it enough to be able to maintain that potential that it has. It's not going to reach full potential. And so by utilizing the NDVI plus the reference strips, we're able to be able to maximize our yield potential and optimize our nitrogen rates based on a nitrogen demand, and allowing the crops to tell us when nitrogen is actually needed. So we use a model that's not much different than a crop model. We may start out with a general reference strip model like we just showed you. But we're able to work with you and fit them to your specific environment and soils or specific crops. This is a scalable model that can also be modified to fit specific crops and additional factors such as tiller counts or cotton boll counts. As an example, we've been doing some stuff with cotton, where we're taking the NDVI and cotton boll counts to be able to predict cotton seed yields. And so with the nitrogen in the soil, these are our reference strips, whether that's a zero check or an enriched strip. And we let the crop tell us what that yield potential it can reach or what it cannot reach, and let us know what is available to the crop. So there's no need to pull soil samples, because the crop is going to let you know when that nitrogen is needed. And utilizing and using these reference strips, this really creates transparency between the agronomist and the grower, and it opens up, the door for communication. And so this transparency is going to be able to create trust. And once this trust is built, the greater the grower loyalty is gained, and opens that door to introduce more technologies and solutions to the grower. And so if they're struggling to be able to get growers to adopt certain practices, then work on being able to get more transparency into their service and to their program. And there has to be a way to build this trust with the grower so that the rate of technology can be adopted faster. And so a reference strip, excuse me, is the simplest and a low to no cost, minimal risk way to be able to do this. And so by applying, nitrogen when the crop shows that it's needed based on these reference strips, and we're able to improve nitrogen use efficiency. If it's applied prior to the demand before these strips are showing up, that nitrogen is going to sit out there where it's awaiting and can be lost in multiple different loss pathways. So what does this method look like in action? Here's an example of a grower out in Kansas who spent a total of about 10 hours putting out reference strips or enriched strips and collecting green seeker data. He had a net return of $42,000 because the SPNRC reduced the nitrogen rate based on that response to the enriched strip. So the demand of nitrogen was less than what he usually applied year after year. And so the dollars per hour on the time that he took to get the labor it took to get these strips out and collect that green seeker data turned out to be $4,200 per hour. And on average, he had a $19 per acre across ROI across these 2,200 acres. And the yield potential that was predicted was within 3 to 4 bushels of the final yield as well. And so on average, using these methods, have an average ROI of $10 per acre in wheat and around $20 an acre in corn. And so it doesn't take a lot of time to be able to get our methods out and collect the data, and we'll also work with you to be able to determine the best way to implement our methods into your operation. But the dollars per hour it takes to use our methods shows to be worth the time. So our take home here, there are several different approaches to nitrogen management, and all are going to be typically linked back to the Stanford equation, most of which are trying to define or predict nitrogen in the crop, nitrogen in the soil, or NUE. To accurately determine these values, in-season site-specific information is needed. Now, our model of using NDVI plus reference strips allows us to get this information and apply a site-specific recommendation while incorporating all components of the Stanford equation. We're able to customize YPN models to accurately predict yield potential, utilizing the reference strips, which lets us let the crop tell us when nitrogen is in demand, so we are not applying nitrogen when it's not needed and leaving that out in the field to be lost. And by following our 4R stewardship, we were able to improve our nitrogen use efficiency. Our methods allow the field to do the talking and make recommendations based on soil nutrient, plant demand, and spatial variability to meet site-specific needs, limit field losses, and improve economic and environmental sustainability, which are all going to be documented and recorded, improved management practices for government regulations and to be able to better communicate the agronomist value to the grower. So if you'd like to look at any of the resources that we used in this presentation, they are all available at ninjaag.com/resources. I really appreciate everybody hopping on and going over this nitrogen rates with us today. If you have any questions that were not answered today, you can give me a call. Here's my cell phone number along with my email, but you can send those directly to me. But that's all I had for everybody today. So thank you guys, and looking forward to some questions here.
Does anybody have any questions for Tyler or anybody?
We've had a few that have emailed in some questions. So how does this model include the weather?
That's a good question, because weather is what we talked about quite a bit. here. And so this model actually includes growing degree days, which is going to let these crop growth patterns, determine the impact of the environment. And so we're utilizing these GDDs within this model.
Tyler, I've got one from an email as well.
Okay.
How does an EJAG model include all components of the Stanford equation?
Yeah, so that goes back to with nitrogen uptake, we are utilizing a yield potential model to be able to, that's customizable to be able to accurately predict yield potential. So that's our nitrogen uptake, the yield. Soil nitrogen, that's the reference strips, being able to identify that nitrogen demand and what that nitrogen in the soil actually is. And then the NUE, the fertilizer efficiency, sometimes our source and our placement is going to be locked in. And so with using in-season applications, we're able to improve that NUE. But this also can be adjusted based on whether that's specific methods, source, or soils, if they think that there might be a higher NUE there. Great questions.
I got another one emailed in. How is the 4R stewardship being used in the Ninja Ag model?
Yeah, so that kind of goes back and ties in to our last question, to where those in-season applications are improving that NUE as well. So our source and our placement might be locked in, but we're able to adjust and modify these NUEs based on those methods that are being used.
Tyler, I'm right in the middle of winter wheat country here in Kiowa. Is it too late to put out strips now, or can I put them out now and get a reference on them, or what do you suggest?
Absolutely. So winter wheat's really unique to where we're able to delay these applications of reference strips in the fall. So after planting, there's still some time to get those reference strips out, typically 30-day window. But yeah, there's plenty of time to be able to get those in-rate strips out right now in winter wheat.
What kind of rate would you suggest me putting on an in-rate strip?
In-rate strip is going to be around a 40 or 50 pound increase over your farmer practice, or whatever the rest of that field is being applied, is what we recommend.
Okay, thank you.
I have another emailed in question. How are reference strips identifying fertilizer efficiency?
Yeah, so the reference strips are actually showing that the efficiency of that pre-plant application, whether that's the response of that in-rate strip or the lack of response to nitrogen.